Right. Hello and good afternoon to everybody out there on the internet. Thank you for coming to another Tech Talks webinar presented by the Teesside Area Local Committee for the Institute of Mechanical Engineers. I hope you can all hear me. So today's talk is given by Andy Normand and Jag Gattu. Andy comes from Encora Energy. He's a chartered mechanical engineer. And Jag is the founder and CEO of UptimeAI. And today's talk is about the myth and reality, AI for plant monitoring and bypassing the pilot purgatory. Now, I know that this is quite an exciting area of study, and there's some real interesting technology going to be presented here today. It is predominantly, it is applicable to all sorts of industries, not just process plants like power stations and chemical works and such like, but also to many other manufacturing and operational equipment out there. But I'll let Andy and Jag talk to you about that. Now, the local area panel has got a couple more events coming up. The next event is on the 7th of October. I hope you can join if you're interested. And this is you and your continuing professional development. Achieve your continuing professional development goals. And then we've got another talk on the PDP, and number 2. That's preparing for your interview, and that's taking place on the 12th of October. Well, on behalf of the panel, we're always interested in putting on talks, and we're always keen to get people involved. So if you live in the Teesside area, please, we're always looking for new panel members, so you can get in touch with Andy Stevenson at Teesside Chair at the IMechE near you.org. And we're also, even if you're not living in the Teesside area, anywhere in the world, we are interested in putting on your talk. If you've got something interesting to tell us, please get in touch, and we'd love to put you on a forum like this. Right, I'll let Andy and Jag introduce themselves, and I'm going to hand over to Andy now.
Thanks very much, Keith, and thank you and the IMechE and Teesside for hosting this event. We really appreciate it. First of all, just a quick introduction as to who I am. My name is Andy Normand. I've been in maintenance and reliability for about 17 plus years now. Started with BP and some upstream and refining. I then moved into the consulting arm of KBC and traveled the world helping people with their maintenance and reliability issues and improvements. I'm now based back in the UK and working for Encora Energy. Now, Encora, they develop, operate and maintain a number of power generation facilities in the UK. And my role within Encora is really leading our partnership with UptimeAI, and that kind of comes in two parts. That's about using their systems to be able to make some improvements and benefits on the Encora facilities, but because we love them so much, and we saw the opportunity for them to operate much more widely, and so we're acting as the agent for them within the UK and European market to make sure that these great systems are used as widely as possible. And we're really lucky today to have Jag Gattu, who's the founder and CEO of UptimeAI, live from California. So Jag, are you able to give yourself a short introduction?
Yeah, definitely. Thanks, Andy. Thank you, IMechE, and good morning, good afternoon, good evening, everyone who's joining from all around the world. Thanks for tuning in. I am Jag Gattu. I'm the founder and CEO of UptimeAI. We are based out of, we're headquartered out in San Francisco, US, and we offer AI-based virtual expert for plant monitoring in manufacturing and process industries. Now, my background, by education, I'm a mechanical engineer. I spent about half my career, about a decade, doing hands-on industrial data analytics with a wide range of industries, all the way from automotive like Caterpillar, Bobcat, Toyota, to U.S. Air Force, NASA, Boeing, as well as medical devices, pharma, and energy and oil and gas companies as well. So I have several patents in the space, and after that first half, I did my business degree and then joined GE in a more commercial role, where I managed some of their product lines in the space of smart instrumentation, plant monitoring solution software, as well as their predictive maintenance software. During which I worked with several of the supermajors in process as well as other manufacturing industries. And those are the insights that we're going to bring into this session. So really looking forward to an exciting session. Back to you,
Thanks very much, Jag. Thanks very much, Jag. So the way this is going to work is I'm going to start off and I'll give some general non-specific artificial intelligence background, some context, and some definitions of terms. And then I'll pass over to Jag to talk more specifically about really the domain that we're most interested in, which is plant monitoring. The first thing we're going to do, though, is we're going to get you to answer a short poll, because we want to be able to differentiate between some terms. So hopefully, Fiona, if you're able to trigger the poll, we want to be able to get you to answer from your experience of dealing with artificial intelligence. Are you clear, and how clear are the people that you've dealt with on the difference between the terms machine learning, deep learning, and artificial intelligence? And I'll come back to that in another couple of slides, but if you could answer that poll, that'd be great. Thank you. So first of all, let's start talking about what we really mean by artificial intelligence. That's the ability of computer systems to be able to mimic some of the functions or mimic the functions associated with human thinking, such as learning and problem solving. Now, when we talk about artificial intelligence, a lot of people will gravitate towards a more general artificial intelligence, and that's really the ability to be able to think and apply learning and solving across a great range of different things, and be able to jump between different contexts, understand context from the issues that they're dealing with, and that's not a technology that really is available at the moment. And so we need to be careful that we're not setting up our expectations for that, because that's a very much a future-looking thing, and that's something that no one has. But what we can talk about, and what we will be talking about in this presentation, is what we would term narrow artificial intelligence, narrow AI, where we're talking about artificial intelligence that is designed for specific types of problems and is really learning and solving within that particular context. And some of those can involve things like driving of autonomous cars. It's the recommendations that you'll get through Netflix will be driven by those narrow problem-solving, learning artificial intelligence. So when we're talking to people about artificial intelligence, one of the questions that often comes up is really about is there real benefits in artificial intelligence, or is it all just hype and hyperbole? And part of the reasons why people think there's a lot of hype is because there have been a lot of high-profile cases where there's been a lot of fanfare around AI, but it just hasn't met the expectations. And later on in my section, I'll talk about some of the reasons for that and go through a few of those really high-profile failures of AI. But the other reason why people tend to think it might be hype is because they're really thinking about general AI and that ability to do all of that jumping between context. But in reality, all of the benefits and there are huge benefits are very much there in that narrow AI capability. When we're talking about specific learning and problem solving within specific contexts, there's really some huge benefits to be made. And there are three examples in the slide that hopefully you can all see, where there are specific tasks, specific contexts where AI has done incredible things. Now, This data is all taken from Stanford University's AI Index paper. And the things that it's worthwhile looking at there is just to say that in those examples, you can see that the artificial intelligence is either getting very close to human performance, matching human performance, or in some cases actually exceeding human performance. And that's before you even take into consideration all the advantages that AI has that humans can't do. You know, it's available 24/7. It's got a much greater ability to take in more data, and of course, it doesn't get grumpy when it doesn't have its coffee in the morning. So there are real advantages there in AI, but we need to be aware of the context in which we're dealing with them. The other thing that's worthwhile noting is that some of these systems, and you can see the dates there, they've only been around for maybe 5 to 10 years. It's a very new thing to really work at the higher levels of artificial intelligence. And if someone's talking to you about the systems that they're using in the context of artificial intelligence, and they're talking about having had these systems for more than that 10 years, chances are they're not really talking about artificial intelligence in the way that we might consider, and they're talking about something slightly different. And that is why we wanted to be able to get that, to go back to the poll that we got you to do a few minutes ago, and be clear about some of the terminologies that we might use. Now, I don't know, Fiona, whether you're able to show the results of the poll. I have some information in front of me which says that fully understands 11.5%, some awareness nearly 70%, and unclear, unaware 19%. So it's clear that these terms are kind of known. People are aware that these terms are around, but really exactly defining them and be clear about what they are is not necessarily there. So what I like to do is be able to define these in fairly general terms, and the example I'll use actually will be around image recognition, because it's quite a good topic to be able to get these contexts. When Jag uses these terms, and he'll put them into much more the context of plant monitoring when he talks later on. So first of all, let's talk about machine learning. This is one of the oldest applications. And machine learning is about extracting insights with human support. So in that particular example of image classification, say, for example, you have a number of pictures of maybe birds and a number of pictures of cats, and you want to divide them between them. You can upload those images, but you also, in machine learning, need to be able to define what it is that you're trying to classify on. So you could say that the things with wings are the birds, and the things with 4 legs are the cats. And if you can define that accurately enough, it will be able to sort through those and say this is wings, there's some legs, and it will essentially be able to classify. But that really depends on your ability as a user to be able to really define what those features are that it can classify with. And when you're talking about birds and cats, that's maybe relatively easy. But when you're talking about maybe cats and dogs, well, they're both kind of, well, approximately the same size, or can be. They're both furry, they've got the same number of legs, they've got a tail, and well, how do you define that in a way that is really, capable of for a system to use? And we all as humans can do that, and we learn as babies to be able to do that. And maybe we can't necessarily be able to define them, but we just kind of know. And that's where you get the next stage, which is deep learning. And deep learning will then not only be able to classify, but will work out for itself what are the features that it will use to be able to make those classifications. In the training of those tools, it will be able to figure out for itself what it is that makes a cat and what it is that makes a dog. And you can feed those images in, and it will be able to work it all out and classify it. But even that is still not then at the same level as a human would do. And that's where you start moving on to artificial intelligence, because the big difference there is when you're having to deal with uncertainty, things that you weren't expecting. in that system, you're feeding in cats and you're feeding in dogs. Well, what happens if suddenly there's a picture of a cow? Now, humans don't, and you don't want your system to be able to say, well, that's more like a dog than it is a cat, so I'm going to call it a dog. That's not overly useful, or at least it has some uses, but it is obviously very constrained. So what we want when we talk about artificial intelligence, and that's where we're going to be talking about artificial intelligence and the level that UptimeAI are working at, is actually it will be able to understand those new situations. It will be able to understand the new things that come in and get some user feedback in terms of that, and be able to continuously learn and develop its own understanding. So it's very much worthwhile being able to be clear on those terms and know the limitations in terms of the amount of initial input you have to do in order to figure out what those features are, and the amount of uncertainty that it can deal with. That's why artificial intelligence, as we talk about it, is more than just machine learning and deep learning. So the other thing that we need to be aware about is whether AI is just a black box, and whether actually it's capable of explaining what the outputs are it's got. In some industries, this may be fine. There are some easier to understand examples where you can plug the data in, it will give you an answer, and that will be fine. In plant monitoring and other complex situations, you want to be able to explain the answers you've got. And that's really about getting the right domain knowledge in there to really set up the systems in a way that will be set for the context and the problems you're trying to solve. So it's another thing that we really need to be aware of when we're talking about artificial intelligence, and something that is worthwhile noting. I said earlier that I would talk about some of the high-profile failures that there have been with artificial intelligence, and they can broadly be grouped into three separate areas. One is bad models that are just not capable of handling the complexity of the task that's been set. A lack of domain knowledge, meaning that they're not actually able to explain what's going on and the solutions that it's providing. And finally, the third one is just that lack of user feedback. It's not able to continuously learn and deal with those additional complications that are unforeseen. So in terms of bad models, a great example there is the first release of Siri. Obviously, Apple released Siri as the greatest thing ever, as they do for everything. And Siri's got a lot better, but in those first releases, if you used it at the time, you realize that actually the voice recognition is not as good as it really needed to be, and it wasn't actually able to answer those questions as well as it would need to be. It just didn't match expectations. As I say, now a lot better, but a disappointing entry for Siri, just due to that inability to be able to handle the complexity. The example for lack of domain knowledge is IBM Watson's medical use and their cancer cure. It was just essentially a fundamental lack of understanding about what is really required. Once again, a lot of money and fanfare was sunk into this at the beginning, but it didn't meet expectations, because when you go and talk to a doctor, you don't really just want an answer. What you want to know is kind of be able to explain what's going on. And the systems that they set up with IBM just weren't able to do that in a way that was satisfactory and did revolutionize the medical industry as hoped. My example for lack of user feedback is Tay, the Microsoft chatbot, which was released a few years ago. And the idea was that you would be able to chat along to this thing online, and it would, it would talk back, and it would learn from the conversations that it would have and mimic back that conversations and get more and more sophisticated and human-like conversations. unfortunately, while it was able to mimic back conversations, what it wasn't doing was learning what is appropriate, what's appropriate language, and be able to continually know what it should be producing, not just mimicking back the things that were entered into it. And what that means is that, as the internet has a tendency to do, people realize that you could just feed in absolutely the most awful, horrible, offensive language you could into this thing, and it would just start repeating it back. And very quickly, I think within a day, it turned from this nice, wonderful little program to talk to really the embodiment of the worst parts, of the darkest parts of the internet, and was quickly taken offline by Microsoft with red faces all around. So I'm now going to pass over to Jag, but just to kind of recap the things that I've hoped you've got from this is we need to be very clear about the terms that we're using in terms of what artificial intelligence actually is. We need to be clear that it's narrow artificial intelligence within a particular context, and that we need models that can handle the complexity that is required. We need some level of explainability out of it, otherwise the system just is not usable in the correct way, and we need to be able to continuously learn and benefit from lack of user feedback. So I'm going to pass over to Jag now to talk more specifically about what this means for plant monitoring. Jag, are you there?
Yep. Thanks, Andy. I think that was a great introduction about the general terms about AI. Now that you have seen what are the three key elements that make a successful AI application, right? And the lack of those can make it, can cause failures. Now, what we're going to do is we're going to take that knowledge and we're going to start applying that to the use case of plant monitoring. And as I go through the slides, what I'm going to do is I'm going to talk about the evolution of the different solutions in the plant monitoring. And I'm going to take this towards the AI applications for plant monitoring. And I'm going to use AI Expert, which is the solution that UptimeAI offers for plant monitoring. And I'm going to use that as an example to talk about the capabilities and how those capabilities can add additional value for the customers. And also we'll take a few case studies to explain and to show how they can be put in practice, right? The capabilities and the technology that we're talking about. Now, before we do that, I also want to take a quick poll from the audience in terms of can you recognize the differences between AI platforms and AI applications? I'm sure you must have heard a lot of, or you must have heard or seen material out on the web. Some of them call themselves as AI platforms, some of them call as AI applications. So just trying to get a gauge in terms of whether you're aware of the differences between AI platforms and AI applications. We'll just take a 30-second break to give you all time to just put your answers, and then we'll continue the presentation. In the meantime, I also want to make a quick note that you can all post questions, submit questions via the Ask a Question in the auditorium, and we'll take all the questions towards the end of the presentation, and we'll address those specifically. Okay, now, okay. 10 more seconds, and we can get back. Okay, great. So I got the results from the poll, and the answers are, so the question again is, can you recognize the differences between AI platforms and AI applications? And the results are, 18% or 19% say they fully understand. 37% say there is some awareness, but not completely. And a massive 43% say it's unclear. It's unclear as to what those differences are. Now, this is not. This is very common in what we see when we talk to customers, when we talk to clients or engineers around the world, that in general, there is some amount of confusion between the AI platforms versus the AI applications. And we see, even in the poll, we see about close to 80% of the audience are either unaware or limited awareness about the difference between these two. So what we're going to do is we're going to go into we're going to start covering the evolution of the plant monitoring solutions. And as I do that, I'm going to talk a bit more in depth about the AI platforms and the AI applications to clarify, right? So if you look at the plant monitoring solutions, what we see on the left-hand side, they are the traditional plant monitoring solutions, right? So on at the bottom, you have the threshold-based condition monitoring, where you take a single signal and you define a specific threshold. And if the signal crosses that threshold, then there is an alarm, right? Pretty simple. Then in the 1980s, when the rule-based predictive maintenance solutions were popularized, where you, instead of taking one signal at a time, you're taking maybe tens of signals, or maybe 10, 20, 30 signals at a time, and still the user or some expert is defining the rules as to how these signals should behave to be able to represent a failure, right? The common thing between these two is the fact that it still requires manual effort to define these rules. Now, let's say you have a plant where you have 100,000 sensors, right? It is not practical to define these rules for 100,000 sensors, or even maybe 10,000 sensors for that matter, right? Which is why these solutions typically are only used on maybe 10 to 20% of the sensors in the plant, and the rest of the 80%, 90% of the data that you have in the plant are typically not really used. Now, on the other hand, let's say you take an equipment which has maybe 100 sensors, right? And now you define rules on maybe 50 of these sensors. And typically, if there's a problem with that equipment, multiple sensors will go over these thresholds. So what will happen is you will get multiple alarms. So this is the second common complaint about these solutions, is that the number of alarms. So because of this high number of alarms and the high amount of manual effort, typically these solutions are used only for on the 10 to 20% of the data and the equipment in the plant. Now, on the right-hand side, what you have is essentially the new category of solutions, right? Here you have the AI platforms and the AI applications. Now, first and foremost, AI platforms are not the same as AI applications, right? So let's be clear on that one. Now, AI platforms essentially are targeted to our solutions where you can build models for specific problems. So these are targeted towards either your software engineers, IT, or data scientists who can actually build models. What they really lack is the capability or the domain knowledge and the workflows that, as Andy mentioned, are key to developing a successful solution for plant monitoring. So one of the key aspects here that is worth pointing out is that in plant monitoring, right? In plant monitoring, the difference between a simple IT and operational technology, which is essentially technologies used in the plant, is huge. And the difference comes from that domain knowledge and the workflows, right? And so a lot of times what I've seen time and time again with customers tend to underestimate the leap that is or the effort needed to take simply a model and essentially add the domain knowledge and the workflows to make it into a full-fledged application. And this is the reason why, McKinsey points out that 70% of the customers who started off with pilots on platforms, they are stuck with pilots, because once you do a pilot, you then realize that the amount of effort and the cost it takes to actually build a full-fledged, solution for the full plant is really, really expensive, right? And that's why AI platforms, they're not able to handle that unknown failures as well as changing conditions. They're just a model for that particular problem, but not necessarily a full-fledged solution for the plant. On the other hand, AI application or purpose-built AI application for plant monitoring should bring the three key elements that Andy mentioned that are necessary in a successful AI solution, right? So that it can not only handle complex problems which require maybe thousands of signals or hundreds and thousands of signals, but also it can handle the continuous changing conditions as well as unknown failures that might come up in a plant. Now, what we're going to do is we're going to go into we're going to take the AI expert as an example for an AI application for plant monitoring, and we're going to talk deeper into each one of these, into the additional value that it can bring. Now, as we mentioned, right, with this AI expert, the key aspects are the ability to bring in AI, the domain knowledge, and the integrated workflows. And it's not enough to just have these in isolation, but it's very important to be able to stitch them together in a way that each one is able to connect and feed off into the other, right? And thereby it becomes a holistic solution as opposed to just a particular model or just a failure mode, right? By stitching these together and integrating them together, now you have a solution which can, number one, it should be able to address complex problems. Second, it should be able to explain the problems. And third, it should be also able to learn continuously to be able to handle unknown or changing conditions. And the reason why these capabilities are important is because, remember, the definition of AI is really about how the solution can bring in some of the concepts of what a human can do, which is the learnability and the explainability and problem-solving capabilities. Now, in order to get those capabilities, you need these three areas covered, right? And thereby, now you have a solution which is starting to mimic a human expert and then give you the additional benefits of almost reduction in the number of alarms by 2 to 5 times, and reducing the manual effort and reducing the time it takes to start acting on some of these problems in the plants, right? Now we're going to let's dig deeper into each one of these capabilities that we're highlighting here and what we mean by these, right? So when we take the when we talk about complexity in a plant, right, we're talking about the interrelations between the hundreds of equipment that are working in together, right? So we are talking about the interrelations between not only the different equipment, but also the interrelations between the process and the mechanical parameters, right? Now I'm going to take a couple of scenarios here to explain the concept. So let's say you have a motor that is driving a pump, right? And they both are connected, and let's say in scenario one, you have a solution where you're monitoring the motor and the pump separately. Now let's say there is a problem with the motor where you're seeing high vibration, and now that vibration is passed on to the pump, and now you see problem with the operation in both the equipment. Then you see 2 separate alarms, right? One for the motor, one for the pump. So this is essentially, if you monitor a lot of the equipment in isolation, then you do get a lot of alarms for the same problem, right? Now in scenario 2, let's say you are only monitoring pump but not the motor, right? In that case, even though the problem is starting with the motor and the vibration starts with the motor, you cannot detect until that problem actually propagates to the pump, and only then you will catch that problem as a vibration problem in the pump. It still doesn't tell you where to fix it because the fix is in the motor, right? So there, what you're doing is you're losing the opportunity to fix the problem before the problem actually manifests in maybe some of your critical equipment, right? So those are the 2 common challenges with traditional approaches which cannot handle the complexity of the interrelations. Unlike these, an AI application should be able to handle the complexity of these interrelations using a more system approach, right? So with an AI expert, we use a more system approach where we look at the interrelations between the equipment, and thereby we can provide just one specific alarm which indicates where the problem is coming from, right? And and by doing that, now you're able to address more complex problems, identify them early enough, and also with less number of alarms. So then, we talked also about the explainability. Right? What do we mean by explainability? See, in plant monitoring, the users are essentially the plant engineers or the field engineers who are operating the plant. And for them, when the solution tells that there is an issue, the solution should be able to tell them that, hey, there might be a filter plugging problem. Go check the filter and see if it needs to be replaced, right? That is the way the end user or the plant engineer understands understands that language. Instead of saying that the pressure signal is over 90th percentile, so that and throwing that as an alarm, right? And that is the difference between explaining the problem in a way that the end user and the plant engineer understands versus talking in terms of pure mathematical terms, right? And the way a AI-based application can bring that is essentially using the domain knowledge within that space. So, for example, with an AI expert, what we do is we bring in the domain knowledge, and what we mean by domain knowledge is the understanding of the different types of equipment in manufacturing and process, the types of failures that can happen within the equipment, and then the types of the symptoms that represent the failures, as well as the mitigation steps that can be taken to address those failures, right? And by building that knowledge base for over 100 plus equipment into the application, now we're able to specifically, not only identify a problem, but also explain that, hey, this is essentially a particular type of, filter plugging issue or something else, right? Thereby, now we're able to help the engineer understand what the solution is telling them, whether it is correct or not, and then take the necessary action, so that the user now is focusing more on fixing the issue, understanding and fixing the issue, as opposed to just identifying and triaging the alarms. Now, moving on to the next one, which is the continuous learning aspect, right? And why is this important from the context of plant monitoring? So if you take let's say if you take plant monitoring, we know that the conditions in the plant can continuously evolve, right? Unlike maybe a credit card swipe, where the type of data that you get is probably very, very consistent, and the data quality is also consistent. In the plant monitoring, in the plant operations world, we know that the data can be bad. We know that sensors can go bad all the time, as well as calibration issues can happen. You can actually do some maintenance, replace a bearing that changes the operating profile of the equipment. Or maybe you just got a new set of raw materials from a new batch, right? And these are all the changes that are continuously happening in a plant. So if you are focusing on just a very, very accurate model and that's it, it's not going to be enough, because in given a month or 2 months or 3 months, all these models are going to go out of sync, and they're not going to be operational. They're not going to give you the right results. And so that's why it's important to have that feedback loop, wherein by looking at new sensor data, by looking at taking user inputs, by looking at maintenance data or process changes, you should be able to adapt the models so that the models are evolving to unknown or changing conditions. And let's now so we've talked about the three capabilities, or three key elements, right? The ability to address complex issues, then the ability to explain the problems, and then the ability to continuously learn, which are again boiling down the key elements required in a successful AI application. Now let's focus on a few case studies or use cases where we can explain how these specific capabilities can be put into application, right? Put into practice. So, so this is a use case for a petrochemical plant. What you're seeing here is a tower system where you have a tower and you have several supporting equipment around it, including pumps, heat exchangers, valves, and others, right? Now, the customer challenges in this in the system are things like tray plugging within the tower, or pump trips, or efficiency loss, or product quality changes, right? Now, as you can see, there are several equipment within this system. You have about maybe 7 or 8 different pumps, several heat exchangers, valves, and the tower itself. Now, if you monitor each one individually, and let's say you're monitoring the tower, and you see that one of the trays is plugging. However, the cause of that tray plugging could be that the vacuum pump, which is supposed to produce enough vacuum, is not working properly, or it could be because the recirculation loop is not, working properly and cooling enough, right? So the idea is that, again, so to address that high number of alarms and to understand the cause, the customer is essentially using the AI expert solution, where we're looking at this complex system as one entity or one functional unit, and we're able to understand the interrelations between those, so that we can now give them a more, reduce the number of alarms, as well as indicate where the problem is. So let's look at an oil and gas use case where how we did that. So in this case, again, it is a complex system where we have, we're defining the system on the right-hand side, where we have a gas producer, a power turbine, and gearbox and compressor, and essentially the lubrication system, the pumps, the motors, the filtration system, all of these as one single system, right? And in this case, we were able to identify the cooling problem in the turbine weeks in advance, but not only being able to identify the issue, but also being able to point out, which subsystems, right, which specific equipment are actually causing the problem. So in this case, even though the symptoms are being noticed in both the turbine as well as the compartment, we're able to notice that the application is able to show that hey, even the cause is actually from the ventilation system issue within the compartment, right? So again, it's important to how we're able to compress the number of alarms into just one single alarm, and be able to point out that one is essentially an impact or an effect versus the other being the cause. Now, this is another case study where, for a power generation company, where the power generation plant experienced a unexpected failure in the generator, and that led to 45 days of downtime and significant revenue loss. Now, the customer also has 5 other generators in the plant, and they were concerned that something like this or these type of failures might also happen with their other 5 generators. So in order to understand how they can prevent these type of failures, they went to their OEM who manufactured the generator, and then they also went to a third-party engineering research company. However, they weren't able to get satisfactory answers. And then they came to, they wanted to use a more advanced solution. So they tried our AI expert solution, which is the AI application here, and where we were able to take in the data, the operating data for the generator, and we were able to show how the application could have predicted the problem months in advance with high accuracy. We also want to point out the accuracy point here, that what we see with AI applications, if you're doing it correctly, with even 5 years of data for a particular system, you should be limited. You should be getting very limited alarms. We're talking about maybe 10, 15, 20 alarms in 5-year period, where we're talking about 3 to 4 alarms a year, versus some of our customers who are essentially who are using traditional solutions and getting hundreds of alarms a day, right? So in this case, we're able to identify the failure months in advance, but at the same time, we're also able to point out the specific diagnosis for that particular problem. We're able to say what specific failure mode this is, Not only that, we're also pointing out what are the ways to confirm and mitigate this, and point the user to the specific bits of data or the specific patterns in the data that the AI engine is using to make this conclusion, right? Now, once this is presented to the user always has the option to say whether they agree with this or not agree with this, or they have further insights. And that's where the workflows and the continuous learning is extremely important, right? And so what we're doing, so when the alert is shown, the user can then provide their feedback to say whether they agree with this, or whether it is a false alarm, or whether they have done some maintenance work which has actually changed the operating behavior, right? And that will trigger the application to adjust itself to be able to handle those changes. In addition to that, we also are looking at how do you handle unknown failures, right? Again, when the application shows that identifies or diagnoses a specific failure, or if the user feels that this is a completely new type of failure that has never been noticed, then the user can also add their own failure modes, thereby, again, that again goes back into the application. And so the next time the same issue happens, the application is going to tell them that this is the new type of failure, and not say that it doesn't know, right? And the third part about learning and continuous learning, why it is so important, is because notice that a lot of the large organizations also have struggle with consistency across the different plants, right? And so with an AI-based application, as the users are using the solution, so for example, you get a specific type of failure and the users are particularly selecting a type of mitigation step, right? Maybe if there's a leak, there's an ultrasonic tool to test the leak, or maybe there's a candlelight test. But given the organization's best practices, maybe every time the user is always selecting the recommendation to use an ultrasonic device to test for the leak, then the application notices that and automatically puts that recommendation at the top of the list. Thereby, when you have a less experienced engineer, or maybe a new plant which is not used to the ways the organization maintains its equipment, the solution already shows that this is the recommended top recommended mitigation step. Again, once again, that essentially enables the application, the AI application, to learn and extract best practices so that they can be made available to across different sites and different users. So to summarize, what we have seen is, first thing, we've seen that with AI you can get additional value. When we talk about AI applications, you're using AI because from a business standpoint you should be able to get additional value, right? That's the reason why we're going and we're trying to use a new technology. We've also seen the differences between the traditional solutions and also the differences between the platforms which are more model focused versus a AI application, which is essentially bringing in all the three key ingredients that make a successful plant monitoring solution. And those are the ability to handle complex systems with less number of alarms, the ability to explain the problems in a way that the end user, the plant engineer, can understand and take actions, and the ability to handle unknown conditions, unknown failures, as well as changing conditions. And because of the capability to have this high level of automation, and also to provide that explainability so that to reduce the amount of manual effort, now you can take these solutions to cover your 100% of the plant. And that's what we're doing with some of the customers we're working with, where we are covering the entire plant, all the data, all the sensors, all the equipment. And because of that, we are now able to handle the complex issues more in advance, thereby providing them more availability. Also, we're able to provide them more productivity gains because of less touch points with maintaining the application, rather than focusing on making the business decisions. And that's why we see about a true AI-based application should be able to give an additional benefit, almost twice as much benefit as a traditional solution, and that's what we are noticing. So I think, hopefully this has been helpful for you, for everyone on the call who are interested in AI and how AI can add additional value for plant monitoring. And with that, I'm gonna turn it over to Q&A. Okay, so
hello.
Yeah.
Sorry. Yes. Hi. Yes, I am. Yeah, I had another colleague in the office also listening at the same time. I didn't really want to get a feedback loop going because there's a slight delay from what I hear as a presenter versus what the rest of the audience hears out there in the World Wide Web. We have a few questions that have come in, so I'll jump into some. Jag, Andy, I think we should start off with a. So basically, there's two questions that are very similar. Sort of a. Does so when you're looking for plant failures, I mean, how much data do you need to work, to detect a failure, and how does the system really sort of deal with sort of faulty sensors, miscalibration, bad data scenarios, that kind of thing?
Yeah, great question. So, see, the more complex. So with AI, right? We are essentially teaching the engine or the model how the system behaves, and that teaching is being done based on the past or existing historical data, right? Now, when you take a complex problem, when you take the more complex the problem is, the more data that you generally require to train the models. Having said that, the difference between an AI application and just building a model is that with an AI application, you could start off with as little as maybe a week or 2 weeks of data, right? And you can essentially start off with that. And the beauty is, because the model has built-in feedback loop, it will continuously take in new sensor data, it will continuously take in the user feedback and evolve the application to be more and more accurate, right? As opposed to if you don't have enough data to build just a deep learning model, then the model is not going to work because the feedback loop is not built into that model, right? So we have worked with customers where we have just taken 2 weeks of data and deployed the solution, and we have also worked with customers where they have 5 years of data and we have trained it with 5 years of data. So both are completely possible with AI applications. And I think that was the first part of the question. I think the second part has more to do with the data quality. Is that right, Keith?
Yes, yeah, data quality basically. I mean, if the sensors are miscalibrated, what happens? Can you still detect real failures or sift the real failures from what is essentially bad data or loss of signals?
Exactly. So what? So one of the key aspects about plant monitoring is the ability to handle the data quality as well. For example, with AI Expert, the data quality module is a first-class citizen. It's not an afterthought. So before the data can even be used by any of the AI models, there is a lot of cleansing or monitoring that is done on the data quality. So things like missing data, high levels of noise, right, out of range, or paintbrushing, or flat lines. All of these need to be detected, and there are different ways of handling these kind of bad data in using advanced models to be able to handle that bad data and still make sure that you can get good insights about the operations. And it is also very important when you talk about a good AI application to be able to differentiate between what is a sensor and data health issue versus what is actually a operational problem with the operations. I hope that answers that question.
Oh, yep. Thank you. If the audience have any further questions or feedback, please to that one, please pop it in, and we will ask Jag. Right, some other questions on the that have come in. Basically, there was a question regarding different systems and subsystems. How do you model the algorithm for each system, and how does it link directly to the plant monitoring tool, such that a fault in one of the subsystems is easily identified without having to do much task evaluation? From an offshore point of view, this is a complex operation. I know that it's extremely difficult to achieve using an isolated troubleshooting model to identify faults in any of the subsystems or subcomponents. I suppose that also ties in very closely to a sort of, how do you establish a system boundaries? That's another question that's been asked, and very similar to sort of how do you deal with complexity in the system, and how can it be handled credibly? So those three questions are very, very similar. So I don't know whether Jag or Andy, you'd like to comment on that, please.
I didn't quite get the question. Can you just repeat the question? There was some breaking in.
Okay, sorry. Yep. So for a plant with different subsystems and subsystems, how do you model for each of these systems and to be linked directly to the AI plant monitoring tool, such that a fault in one of the subsystems is easily identified without having to do too much task evaluating the entire system of the plant? From an offshore point of view, this is a complex operational area that's extremely difficult to achieve using an isolated troubleshooting module to identify faults in any of the subsystems or subcomponents. And it also sort of ties in quite closely with another two questions that have been asked, which is it possible to express the level of complexity that an application can handle? And how do you establish system boundaries for an AI to get the best out of an AI system?
Yeah. Great question. So yes, the key capability, or the key to successful functionality with doing a system level is, while when you take the data, let's say you take 10,000 sensors and you build a model, it's all right to build a model because you just push the data into the model and the model gets trained, right? However, this is where the integration between the model and the domain knowledge and understanding of the systems come into picture, where you also need to pretty much dissect the insights that you're getting from the model to be able to then separate them into the specific subsystems and the subcomponents, so that at the end of the day, the end user can actually say there is something wrong with my pump, or there's something wrong with my filter, as opposed to saying there's something wrong with my plant, right? In the way, and that's essentially a framework that UptimeAI has built, where we have essentially a structure in which we can take the deep learning or the complex AI models and actually integrate those with the structure of the systems there, and so that we can actually present a more actionable insight. And this is a patent pending technology or proprietary technology that we use to be able to get those insights. And and we have been able to do that successfully for different customers. Now, the second question about I believe is around what was the second question? Sorry,
Sorry, so is it possible to express the level of complexity that an application can handle credibly?
Yeah.
So how complex, is it one big whole plant, I assume, or is it, do you break it down to smaller subsystems?
Understood. So first, I think this goes into the question about how do you break down the systems, or how do you break the plant into different systems, and then also how large can you take of how much complexity can the tool handle. Now, first question is, what we're doing is we are continuously pushing the boundary of the application, right? We're pushing the limits of the application. We have we have taken systems where we have 40 sensors versus 200, and we have done systems where we have 2,000 sensors. These are from as an example, right? so in terms of what is the complexity that it can handle, I think if you talk about a particular system, we have taken systems which have more than 1,000 sensors at once. So we're looking towards where how far we can take that before it'll stop. But in terms of if you look at the complexity within a plant, by breaking the plant into different systems, we can definitely cover as large of a plant as possible. The architecture that we're using from a cloud perspective and the technology underlying stack that we use is specifically designed for plant monitoring, and we know that it is extremely scalable to very, very large installations in the plant. Now, on the topic of how do you define the boundary of a system, so typically we look at these boundaries as large functional systems. So for example, in a power plant, a large system can be taken as a boiler system, right? And typically a boiler is a very large piece of equipment in a power plant. And when you take that boiler system, there are several peripheral equipment that support that particular system, and you take all of those as one functional unit. Similar to how we showed the tower system as an example, where your tower is a central piece central piece of equipment that is being supported by all the peripheral equipment like the pumps, the valves, the condensers, and all of those. And we define the boundary around all of that as one functional unit. And so that's how we separate the plant into multiple systems. Hope that those answered that question.
Thanks, Jag. Yeah, I think that does. But if anyone's got some comments, please feel free to chip back in. Another question. You say you need domain knowledge and to know what the monitoring is doing. How do you deal with uncommon types of equipment? Do you have to build a bespoke AI model, or can you just apply it and see if it works?
Excellent question. So this is again one of the major differences between just a platform versus an AI application, right? In a platform, you're focusing on building models, right? You're focusing on building models for each and every specific equipment or failure or use case. Whereas in a plant monitoring AI application, the structure and the framework of how the models and the domain knowledge and the workflows are working in conjunction to each other is already pre-built. So right now, as I was saying during the presentation, that we've already built a database where we can take 100+ equipment, and all that knowledge base is baked into the AI application. So if you come across a very, very specific piece of equipment that is not covered as part of that 125 pieces of equipment, then we can actually add that equipment into the knowledge base without even having to go into the models or changing the workflows or anything else. And that's how we scale the solution to the full plant. And that's why as we go towards new units or new plants or new equipment, it's not going to be a complete redo of all the effort. It is just a very simple matter of configuration. And that's what we have built as a framework and a structure to be able to add that additional equipment into the application as well.
Okay, thank you, Jag. Right, I mean, there's a couple of questions that are sort of related to how you go about implementing your system. I mean, one of the questions is, do you need a DCS or SCADA historian? And do you need to install any additional hardware for the system?
Yeah. So one of the things we see within a lot of the large manufacturing or heavy industries is that the plants typically they already have a good amount of data to begin with, right? Now that data might be in different locations or different systems, or it might be all centralized in a central historian, right? Both of these are possibilities. So the AI application that we're talking about, the AI expert, we connect to the historian, which is essentially a central database where all the plant operating or sensor data is gathered, right? So we connect to that historian and we pull that data, and then the application uses that data to monitor the plant in a real-time basis. Now, in specific cases where that data is not already in a centralized database, such as a historian or a data lake, then we can bring in partners. We work with several partners who can actually connect, bring that data into a central data lake or a historian, and thereby we can actually use that data to pull in to generate insights. Now, question about do we need additional hardware? See, majority of the times what we see is there's always enough data to be able to generate good amount of value for that customer with the existing data. But at the same time, when we go and work with the customer, we also look at what additional data could be gathered, and what would the additional value of that new data would be, right? So we look at what is the existing data, how we can actually generate insights with the existing data, and at the same time we provide an advisory about these are the additional sensors and this is the additional value that you could get with these sensors, so that if the customer is interested, they would go in and procure additional sensors, and we can bring in partners to do that. But majority of the times we have been able to generate significantly valuable insights with the existing set of information without any additional hardware.
Okay, right. So we've got a sort of a few questions which are a bit more let's say high level about about what the capability of AI, not necessarily around sort of plant monitoring area, but sort of a bit high level. So one of the questions I have is can we use AI in the future to fully control manufacturing plants or sites? Do you think that's possible, or do you think there'll always be a need for a sort of human intervention, or I suppose it's similar to we always thought that we needed a human to drive a car, but plenty of other companies seem to suggest otherwise. So
no, I understand. I think definitely that is going into the more towards the general AI category, because when we talk about operating the plant, there are several aspects, right? Not just identifying either whether there is a problem with an equipment or whether there's an efficiency loss, but there are also aspects about, when do you schedule maintenance, how much inventory do you maintain, how many spare parts do you maintain? There are a lot of other areas as well, right? Now, in general, the trend in the technology is going towards, that bringing that more context aware and being able to take the knowledge from one area to the other. But still, I would say we're probably we're several years, if not decades away from getting to that point of completely automating the manufacturing, completely automating the plants. I think right now what we are looking at, as Andy mentioned, are narrow AI applications which are doing things either as efficiently as a human can do, but with a lot more data, because that is a limitation with humans, right? With a lot more data and a lot more scalability, versus essentially being able to solve any problem within the plant. And right now, the narrow AI applications are, in a way, you can think of these tools, the AI expert, right? He's essentially a virtual expert that brings in the capability of learning and explainability just like a human subject matter expert would, but at the same time combine that human capability with the ability to scale to every single sensor and every single equipment in the plant, so that you have your own personal expert sitting next to you to point out, to guide essentially where things are going wrong, and still give you those enough information so that you can make those judgment decisions. We're not at a point where we can turn the plant to a solution and say just run and go and just sit back. I don't think we're there yet. And I think, since you mentioned about driving, right? Let me also address another. So an analogy I could take is autonomous vehicles and autonomous driving, right? So again, if you are driving in a specific, if you take the autonomous vehicles, the way the cars are learning how to drive themselves is essentially, there are these companies, whether it might be Google or whether it is Tesla or others, they have done enough number of trials in the real world, right? Where they drove the car, and every time the car is making a mistake, they are actually pressing a brake, or they are actually holding the steering and overriding the automatic control, right? And every time every time the user is overriding the system, the application or the AI system knows that there is something wrong that the AI application has done, and it is actually taking that feedback and adjusting it itself, right? Now, they have done to the extent where they have done enough they have put enough miles on the road and in the real world, so that they got to a certain level of fidelity, right? And at that point, they have released the product into the market with autopilot for the Tesla. But still, keep in mind that every time you engage in autopilot, and let's say if you have actually overtaken the automatic control, the system is still taking that feedback and trying to either pass that information back or trying to essentially adjust itself. And that is essentially the true nature of an AI application, where it has to continuously learn and adjust to unknown or unseen conditions. But still, we're not at a point where you can just take a car and sit back and just sleep or lie down versus let the car drive you. We're not still there yet.
Okay, so I mean that's interesting, because I think one of the other questions we've had is sort of talks a lot about open loop processes, and sort of whether AIs can sort of really function without that sort of closing the loop back on itself. I can't think of many sort of process plants that run open loop, but driving is a classic open loop process where a deer can jump out at you, and how it deals with that. So I suppose you have covered that. I don't know if you've got any thoughts on sort of closed loop and open loop processes, or maybe in other manufacturing disciplines where such as machining or sort of type things.
Right. See, I would like to differentiate between a closed and open loop in a process in the process operations versus a closed loop within the AI application, right? Because even in a manufacturing plant, right? The reason why you have closed loop is to be able to handle the noise or the changes in the conditions without sacrificing the efficiency or the consistency in the plant operations, right? If you look at the AI app, so we're not talking about creating control systems or automation systems in the plant, right? That is essentially the automation systems, which are different from the plant monitoring solution that we're talking about, right? Now, when we look at AI applications and the closed loop there, even when we take the car as an example, right? In the old days, maybe 10, 20 years back, the car was an open loop in the sense that you're driving. If a deer comes, you're not seeing. I mean, you as a driver has to take the step, right? Has to take the action. Now with lane changing detection, with blind spot detection, with LiDAR detection around the car, is it really an open loop anymore? I mean, we have to ask ourselves that question, because now if you have a small kid, if you're driving a car and you have a small kid or some animal coming in front of the car, there are cars which actually stop automatically, right? So because of the additionals of the sensorization of the cars that are now in the market, that closed loop is being added, and that closed loop is also the same closed loop that is being used in AI systems to make them autonomous. I hope that answers or clarifies the question.
Okay. No, I think that's great. We don't seem to have any more questions coming through from the attendees, so I think that we should sort of wrap it up. What I'd like to do is on behalf of the Institute of Mechanical Engineers and the local sort of Teesside panel, I'd like to thank you, Jag, and I'd like to thank you, Andy, for putting on what was a genuinely fascinating talk. And yes, if you'd like to just say goodbye yourselves, normally I would get everyone to clap if we had a real audience, but unfortunately I can't really do that. But in a webinar, but I'm sure the attendees will like to thank you as well. Okay, Andy, Jag, anything else?
Yep. I think hopefully you've gotten good takeaways from this, and our contact information is there on the slide that we're sharing. So feel free to reach out to Andy or us at UptimeAI, and we'll be more than happy to follow up. Thanks everyone for joining, and thanks for organizing this.
Okay. Thank you. And I'd just like to say that the recording of this webinar should be available. And you should get a link sent out to you from the Institute. Okay, well, no, thank you for your time. I hope you've enjoyed it, and I look forward to the next tech talk that we put on. Okay, thank you.